In the last session I talked about the 0 strength temperature, the 0 ductility temperature and the liquid impenetration temperature. These are basically important parameters which we have to keep in mind while considering what is the strength or ductility of the solidifying shell. Like what I mentioned was that when solidifying is taking place, so these are the dendrites which are forming in the mushy zone. You have both dendrites as well as liquid steel, and this is of course the total solid shell. That means this temperature corresponds to the liquidus temperature TL. So here the solid fraction is 0, and we have completed the solid fraction say at this location. That means at TSA, that means the actual solidus temperature corresponds to here, and the solid fraction is 1. That means 100% solid, this is 0% solid. Beyond that is liquid steel, and beyond this we have solid shell. So the question is, at what temperature the strength of the solidifying shells strand, what temperature does it develop strength? That is what is important. So I have mentioned that at around solid fraction of 0.7 or 0.75 the strand is developing some strength. When the solid fraction is less than that, that means from solid fraction of 0 to say 0.7 or 0.75, the dendrites have formed, but the liquid steel also is quite substantial amount present. So the strand that does not have strength. So the strength is developing only at a temperature which we call it 0 strength temperature, which corresponds to solid fraction of 0.7. So 70% solid is there, 30% is liquid. The strand is starting to develop strength, and this is the strength, this dotted line. So you see the strength has started developing. Above this temperature, when the solid fraction is less than 0.7, there is no strength in the strand at all. So we are trying to tell you that the strand is developing strength at a solid fraction of 0.7, and then it is increasing as we are coming down. So when we are at the actual solidus temperature, that means the solid fraction is 1, what do you get? You get some strength. But look at the ductility figure, ductility of the strand. Ductility beyond ductility in the range of say this range. That means when the strand has developed strength, but you do not find any ductility. So it has a 0 ductility in this region. So in the temperature range between corresponding to solid fraction of 0.7 and 1, that means when the solid fraction is 70% to 100%, in this temperature region the strand does not have any ductility, but it has some strength. The strength has started at around 0.7 solid fraction. At this temperature, that means at the temperature corresponding to solid fraction of 1, that means when the solidification has just completed, at this region ductility has just started to develop. So in this particular region corresponding to solid fraction of 0.7 to 1, the strand has strength, but it does not have ductility. So what is the implication of that? The implication is this area is very brittle, it is like glass. It has strength, but it does not have any ductility. That means whenever there will be some strain or stress or force which is getting impinged on this solidifying strand or shell, what is going to happen? There will be crack formation, because there is no toughness, no ductility around this temperature. So there will be crack formation. But fortunately, since liquid steel is available between say 0.72 and 0.9, so whenever there is a crack formation, this liquid steel will be available to heal up the cracks. So crack formation will be there because it is brittle, because strength is there, but there is no toughness or ductility. So whatever strain will be impinged getting impinged on the shell, it will cause crack formation. So, crack formation will be there, but between say 0.7 to 0.9 solid fraction, since liquid steel is available, liquid steel will move and heal up those cracks, because liquid steel is available at the surface regions of the dendrites. Interdendritic region, there is sufficient liquid steel. But what happens say along this when solid fraction is say 0.9? So, the dendrites are touching each other. That means, if there is a crack formation in this area, liquid steel cannot penetrate. So, that is why this is called liquid impenetrable temperature. That means, at this temperature, which corresponds to 90% of the solid fraction, what is happening? Liquid steel cannot penetrate, and if there is a crack formation, that crack is going to stay. So, it is a problem for the quality of the cast. Why? Because cracks, whatever is forming because of the brittleness, they are remaining in the cast product. So, there is no chance to heal it. So, therefore, this particular temperature range, that means corresponding to the solid fraction of 0.9 to 1, that means around the actual solidus temperature, this area is called the high temperature brittle range or brittle temperature zone, because as you are coming down in temperature during solidification, there is no ductility here, no ductility beyond this temperature. This is called the zero ductility temperature, and zero strength temperature is around solid fraction of 0.7, we call it ZST. Zero ductility temperature more or less coincides with the actual solidus temperature. That means, at a solid fraction of 1, that means when solidification is just complete, then only the strand starts developing toughness or ductility. So, this temperature region, that means the temperature region near the solidus temperature is really the brittle temperature zone, because here if the cracks are forming, they cannot heal because the liquid steel is not there. So, this is the real zone of or effective zone of brittle temperature, where brittleness, where if there is a crack formation, those will remain. So, we have to be very careful about this temperature region, which is the brittle temperature region at high temperature. So, this is called the zero ductility temperature. From here only ductility starts improving. That means, even slightly below this temperature, ductility is also quite low. So, there is a chance of crack formation around this temperature region. That means, around the actual solidus temperature, the brittle zone exists. So, we have to be very careful while the strand is getting cooled during solidification. This temperature region we have to be very careful about. So, brittle temperature zone near actual solidus, that means between LIT and TSA, that means in the solid fraction region of 0.9 to 1, it is 0 ductility, and beyond this ductility is slowly increasing. So, even slightly lower than this temperature, ductility is also quite low. So, this temperature region is called the brittle temperature zone near actual solidus. So, we have to be very careful about this particular temperature. Then I had talked about how the carbon is affecting this brittle temperature region during solidification. I have talked about the brittle temperature region, which is near the actual solidus region between solid fraction of 0.9 and solid fraction of 1. So, let us see with carbon how does it change, how does it vary with carbon, because definitely it will change with carbon, because why? Because the actual solidus is also changing because of the carbon content, because of the mode of solidification. So, this brittle temperature region also is changing with carbon. Now, let us see how does it change. So, for a carbon content which is less than say C1 a particular carbon content, or less than this, what is happening? How is the solidification taking place? Liquid, then it comes to delta plus liquid, that means delta solidification. and then solidification is complete. There is no sign of austenite till then. So, solid is totally delta after solidification. After certain temperature only, when the temperature is coming down, then only gamma is forming. So, the solidification is totally through delta, and whenever total solidification is complete, we have 100% delta, and when the temperature is coming down after certain temperature interval only, we get delta to gamma transformation in solid state. But in liquid state, that means during solidification, there is no gamma, no austenite. So, beyond C1, when we are increasing carbon content above C1, what is happening? Look at here. Solidification initially again through delta mode, then this is the temperature when gamma transformation is starting, delta to gamma, because of the eutectic temperature, because of the eutectic reaction. So, what is happening is delta to gamma is taking place in the brittle temperature region. What is the brittle temperature region? This dotted line and this line. That means at point between 90% solid fraction and 100% solid fraction. So, solidification is getting complete at this particular temperature. So, here within this temperature range above C1, this transformation from delta to gamma is taking place. So, delta to gamma is taking place means I have told you earlier what is the implication. There is a shrinkage from the delta to gamma transformation, and shrinkage means there will be a strain, there will be stress in the solid fraction, solid, whatever solid you have. So, what is going to happen? This stress or strain is adding to the solidification strain or stress. So, at carbon concentration above C1, we are having this transformation delta to gamma in this brittle temperature region. Now, what happens at Cmax? This particular chemistry is around slightly above 0.1, around 0.1 only. The total delta to gamma transformation is taking place in this brittle temperature region. Here, some of the transformation is taking place in brittle temperature region. Here, the maximum transformation for the delta to gamma is taking place in the brittle temperature region. Is it clear? This line is basically delta to gamma transformation line start, and this is complete. So, the start is taking place when C1 is increasing. So, as we are increasing carbon concentration from C1 and going to Cmax, more and more of delta to gamma transformation is taking place in the brittle temperature region. So, at Cmax, maximum transformation from delta to gamma is taking place in the brittle temperature region. This is very important to note. Now, when we are going above Cmax, let us see what is happening. Cmax, I have told you maximum delta to gamma is taking place within this temperature region. This is a delta to gamma transformation complete, and this is the delta to gamma transformation start. So, as you are increasing carbon concentration above Cmax, more than Cmax when you are going. So, again the transformation has started above the brittle temperature region, and some of the transformation you see is happening in the brittle temperature region. Now, look at this figure C2. What is happening here? At C2, the transformation delta to gamma is taking place above this brittle temperature region. The end of the brittle temperature region is coinciding with the end of the delta to gamma transformation is coinciding with the start of the brittle temperature region here. So, that means between C1 and C2, delta to gamma transformation during solidification is taking place in the brittle temperature region. It is starting at C1, it is completing at C2, and the maximum of transformation from delta to gamma is taking place at Cmax within this brittle temperature region. Above C2, what is happening when the carbon concentration is more than C2? The delta to gamma transformation is taking place during solidification, but above the brittle temperature region. It is taking place here when the the constant rather the amount of solid is say about 50%, 60%, 70%, it is taking place. So, it is taking place above the brittle temperature region, which is between solid fraction of 0.9 to 1. Again I am mentioning this temperature region between solid fraction of 0.9 and 1, the temperature between liquid impenetrable temperature LIT and ZDT, zero ductility temperature, which is corresponding to the completion of solidification temperature. This is the actual solidus temperature. So, this is the brittle temperature region. So, this carbon region from C1 to C2 is the carbon concentration we have to be careful about, because why? What is happening? Any steel which is having carbon concentration within this region, delta to gamma transformation during solidification is taking place within the brittle temperature region. So, this is a very critical concentration region we have to be careful about, because there is scope for crack formation in this for this concentration region, and this concentration incidentally is around the 0.1% carbon. It starts slightly lower than 0.1 and continues up to say about maybe 0.2. So, this is the carbon concentration at which point, at which region rather of concentration the delta to gamma transformation is taking place within the brittle temperature region. So, what is the implication? You will find the implication here. Here strain has been calculated and plotted for carbon concentration. In this diagram we had plotted the brittle temperature range during solidification. How is it changing with carbon concentration? So, now we are actually plotting the strain. So, I have told you the shrinkage strain is a combination of 2 or 3 things. One is the thermal strain. Thermal basically consists of 2 components, one is due to solidification and this is due to change in temperature when cooling is taking place during solidification itself, or even less than that, even lower than that. So, this epsilon, that means the strain due to thermal consideration, and this is the strain due to delta to gamma transformation. Now, see what is happening. This is the, I have told you, between C1 and C2 the delta to gamma transformation takes place in the brittle temperature region. That is why you will find the strain beyond lower than C1 it is almost 0, above C2 again it is almost 0, because it is taking place either below this brittle region temperature region or above the brittle temperature region. So, the strain is maximum at Cmax, as I have told you. Why it is maximum? Because all the transformation of delta to gamma is taking place at a concentration of Cmax in the brittle temperature region. So, that is why at Cmax this transformation strain is maximum, at C1 then it is coming down, and less than C1 it is 0, and again also it is coming down from Cmax to C2, and above C2 again it is 0. And this one is the thermal strain. Thermal strain initially at delta solidification it is very low, slightly increasing, and then above 0.2 it is again increasing, because the temperature interval increases because of difference in the or temperature difference between liquidus and actual solidus increases because of 2 factors. First, there is a chemistry effect because of carbon, and also because of microsegregation. So, this will increase beyond say 0.2 is going on increasing. But what is important to note that between C1 and C2 the total strain is quite high. Here beyond 0.2 this thermal strain is increasing, but transformation strain is not there. Below C1 thermal strain is also low and transformation strain is 0. So, less than 0.1, less than C1 the strain is very low. So, the probability of formation of crack in this temperature region, along this brittle temperature region, is almost nil, but between C1 and C2 the probability of crack formation is high and it is maximum at C max. So, that is why we call that peritectic chemistry, that means the chemistry of the carbon at the start of the peritectic reaction. This is the start of the peritectic reaction when delta to gamma transformation is taking place through peritectic reaction during solidification. So, from C1 to C2 is the zone of concern, chemistry area of concern, because here the strain is quite high because of delta to gamma transformation. So, in this brittle temperature region there is a possibility of crack formation. Now, I will be talking about, based on whatever understanding we have developed on the strength and ductility of the strand, solidifying strand. Now, let us try to understand how this solid shell will behave for different concentration of carbon. That means, when initially the shell is forming, what are the forces on it? There are two opposing forces acting on the solid shell. I have told you that depending on the whatever I will be now talking about, there are two opposing forces. One is the ferrostatic force. Ferrostatic force is basically due to the liquid steel which is existing during solidification. This ferrostatic force during solidification pushes the solid shell towards mold. I have told you earlier, this is pushing the solid shell towards the mold, and when you are coming below the mold, it is causing sort of bulging, that means it is pushing the solid shell away from the liquid steel. So, this ferrostatic force pushes the solid shell towards mold or away from the liquid steel. So, what is the sticking or bulging strain? You can calculate this. It depends on the ferrostatic force, it depends on the strength of the shell sigma, and it depends on the actual shell thickness SA square of that. So, shell thickness is very important here. So, higher is the ferrostatic force, that means as you are going to more and more of solidification, that means we are going down, the ferrostatic force is increasing. So, towards the end of solidification, ferrostatic force will increase. So, there will be more of this strain, and also it depends on, it will depend on what? It will depend on the sigma, strength of the shell. If the strength of the shell is more, this strain can be less. That means, what is resisting the ferrostatic strain or force? It is basically the strength of the shell and the solid shell thickness. So, solid shell thickness, if it is thick, it is wide because it is the square root of that. So, it can resist it appreciably. So, the strength of the shell and the thickness of the shell, these two are important parameters to resist this sticking or bulging strain. Why it is called sticking? The solid shell will try to come towards the mold. So, there is a tendency for the mold to stick, tendency for the shell to stick to the mold wall. So, here the role of the thickness of the casting powder, or the mold powder or the mold slag which is formed from the powder, that is very important. So, that has to resist this, that is important, otherwise the shell will try to stick to the mold. So, this is one force. Another is the shrinkage, which is opposing force. This force is acting away from the liquid towards the mold, but the shrinkage, in which direction does it act? It will act towards the liquid steel and away from the mold, opposite to the ferrostatic force. So, now shrinkage is due to what? Due to solidification, due to cooling, and due to transformation from delta ferrite to gamma. So, solidification shrinkage, cooling shrinkage, thermal shrinkage, and transformation shrinkage, all these add together will cause the shell to move away from the wall and towards the mold wall and towards the liquid steel. So, here ferrostatic force is pushing the shell towards the mold away from the liquid steel, and here shrinkage is pushing the shell away from the mold towards the liquid steel. So, these two forces are opposing, these two strains are opposing each other. So, this can be calculated, thermal strain can be calculated, basically coefficient of thermal expansion and the temperature difference between the solidus and the surface temperature, and the and the solidification strain also can be calculated, how much solidification temperature difference is there, all these things can be calculated. And last transparency I have told that this delta to gamma transformation strain also can be calculated. From the density difference between delta and gamma, we can calculate the strain, the shrinkage due to delta to gamma transformation. So, this strain also can be calculated. So, finally, which one is more? The sticking or the bulging strain is more compared to the thermal and transformation strain. If this is so, then there will be sticking or bulging tendency. If reverse is true, that means the strain due to thermal and transformation is more than the bulging strain, then the consequence will be formation of surface depression. So, it is clear now that for certain chemistry there will be sticking or bulging tendency, I will come to it now, and for certain chemistry there will be depression formation. That is why we call it sticking or depression of solidifying shell. There will be either sticking or depression depending on which strain is more, whether bulging strain is more or the shrinkage strain is more. Depending on that, if the bulging strain is more, sticking strain is more, we will have sticking tendency, but we have shrinkage. If the shrinkage strain is more compared to this, we have depression tendency of the solidifying shell. So, these two behavior, sticking or depression, it is intrinsic to the steel chemistry. Steel chemistry will determine how the solidification takes place, what are the solidification constituent delta, or whether it is delta or gamma, whether the chemistry again will dictate how much is the microsegregation, this will dictate what is the actual solidus, this will dictate how thick will be the solid shell and what is the thickness of the mushy zone. So, all this will determine what is the relative sticking or depression behavior for any particular chemistry.